In this video, we'll be talking about free-falling objects and motion graphs. Okay, so first of all objects, regardless of their mass, accelerate at the same rate as they fall freely. And an important point here, if air resistance is neglected. So you take any two objects, drop them from the same height, and they will land at the ground at the same time, assuming air resistance is negligible. Now, for the most part, this works pretty well, but when you get an object, for example, like a sheet of paper, which has very low mass and a lot of surface area, and you drop that, for example, at the same time as a tennis ball, certainly the tennis ball is going to hit first because of the fact that there's so much more air resistance for the sheet of paper. But aside from that, if you're talking about no air resistance, all objects will accelerate at the same rate. Famous experiment done by Galileo, who dropped a feather and a coin in an evacuated chamber and showed that indeed they did hit the ground at the same time. Okay, now objects falling freely accelerate, and this is called the acceleration due to gravity, and the value is 9.8 meters per second squared. So all objects, again, regardless of their mass, as they fall freely, accelerate at this rate. Now, one other point here. Since gravity acts downward, and now we're talking about vertical axis here, not horizontal, we usually say that g is equal to negative 9.8 meters per second squared because it is acting downward. And we're going to be doing some problems, and this is going to be important in the problems, especially when you're dealing with up and down motion. Okay, so here are the same four equations that we saw in the previous lecture for horizontal motion, only they're modified a little bit to work for vertical motion. So this first one here, final velocity equals initial velocity plus gt, g again being the acceleration due to gravity. This one, displacement for an object, notice this is y because we're talking about vertical displacement, so we don't use x, we use y, equals v0t plus 1/2 gt squared. And then the final velocity for an object accelerated for a known displacement, final velocity is equal to the square root of the initial velocity squared plus 2gy. And then this one is unchanged. The average velocity is just equal to initial plus final divided by 2. Now in all of these equations, don't forget that g needs to be negative 9.8 meters per second squared. Okay, we're going to go over a problem here whereby we're going to compute the velocity and displacement for an object as it falls freely for 1 second, 2 seconds, and 3 seconds. So we can use these two equations here. This will allow us to compute the displacement, and this one for the final velocity. Okay, so for 1 second, we're going to start at the initial velocity here is 0. It's being dropped from rest. And so the initial velocity is 0. This whole term here becomes 0. So it's 1/2 times negative 9.8 times 1 second squared. So that comes out to be negative 4.9 meters. So that negative sign indicates that the object is 4.9 meters below the point where it was released. Now the velocity, again the initial velocity is 0, and so the velocity is negative 9.8 meters per second. That negative sign indicates that velocity is downward. Downward being negative, upward being positive. Okay, now we go on to 2 seconds. Same equation, okay? This comes out to be roughly 20 meters to two significant figures, and the velocity is roughly 20 meters per second. And then 3, 44 meters from below the point where it was released, and the velocity was negative 29. Now, the reason I went over this is it illustrates something very important, and that is if you look at how far the object fell during the first second, which was 4.9 meters. And then from the first second to the second second, roughly 15, right? This is 20. 20 minus 5, 4.9 is roughly 15. So it fell 5 meters the first second, and then during the second second, roughly 15. And then during the third second, roughly 24. So as the object falls, each successive second, it falls a greater and greater displacement. And the reason why that is because, again, the object is accelerating. And if it's accelerating, that means its velocity is getting faster. And if the velocity is getting faster, then it's going to cover a bigger and bigger distance each successive time interval. Notice that the velocity, however, increases by 9.8 during each second. So the first one was 9.8, and then this one is roughly 20, and then this one is roughly 29. Okay, so here is one of those problems that I was talking about before, where a ball is being thrown up and it comes back down again. It's being thrown with an initial velocity of 6 meters per second. We want to know how high did it go and how long was it in the air. Okay, so to find the height, we're going to use this formula right here. And one thing you have to recognize is that when it reaches the maximum height, the final velocity is 0. So we set this equal to 0, and we solve for delta y, and that gives us this. Substitute in the values, and we end up with 1.8 meters. Two things about this. Notice, first of all, that it's positive, and it should be positive because the fact that this 1.8 meters is above the point where the ball was released. So therefore, the sign of this should be positive. Okay, now to find the time in the air, we're going to use this formula right here. And for this, we're going to set y equal to 0. And the reason why we set y equal to 0 is because the ball comes up and it's caught again at exactly the same point where it was released. So the net displacement of the ball is 0. So we set y equal to 0, and we're going to solve it by factoring t out. So we factor t out, we get this, plug in the values. Okay, now, the solution, you have to remember that in mathematics, if you multiply two quantities together and the result is 0, one of the two must be 0. So we've got two solutions here. One solution, t equals 0, and the other solution is that this expression is equal to 0. When this is equal to 0, we can then solve for t, and we end up with t is equal to 1.2 seconds. By the way, both of these solutions are valid. The net displacement was 0 at the point where the ball was released, at t is equal to 0, and at 1.2 seconds, at that point the ball was thrown up and it came back down again and it was caught 1.2 seconds later. So both of these solutions are correct, physically correct. All right, now we're going to take a look at some motion graphs. And the first one is a displacement versus time graph. Now, the slope of a displacement versus time graph equals the velocity of the object. Now, take a look at this graph right here. we've got displacement on the y-axis, we've got time on the x-axis, and notice that the position of the object is the same as time passes. So what does that mean? Well, it means that the object is at rest. Its position is not changing as time passes. So it's at rest, its velocity is 0. What's the slope of this line? I think you can see just by inspection that the slope of that line is 0. Now let's take a look at this graph over here. This graph is also displacement versus time graph, and it has a measurable slope. Okay, if we look at the points, we can see that the distance traveled during each successive time interval is equal, and that ends up giving us a straight line. The slope of this line would be equal to the velocity. Notice that slope is equal to rise over run, which in this case is change in displacement over change in time, and that is the definition of velocity, change in displacement over change in time. Okay, now this is a similar thing, only now we've got velocity versus time graphs, and the slope of a velocity versus time graph equals the acceleration of the object. Again, we're going to look at two graphs. This one, velocity versus time, we see that as time passes, the velocity stays the same. The velocity stays the same, it's constant. It's not 0, it's just staying the same, constant value, so therefore it's not accelerating. Remember, acceleration is the rate of change of velocity. This velocity is not changing, so therefore the acceleration is 0. What's the slope of that line? Again, I'm sure you can see that the slope of this is 0. And as we look at this one, now, as time passes, the velocity is increasing, and at each time interval, the velocity seems to be increasing by the same amount, and so therefore we can see that it is uniformly accelerating. The slope of this line would be numerically equal to the acceleration. Slope here would be equal to rise over run, change in velocity divided by the change in time, which is the definition of acceleration. The last graph I would like to show you is again displacement versus time, but this time for uniformly accelerated motion. Okay, so this is the graph. Now, as we said in earlier in this video, for accelerated motion, the distance traveled, or the displacement covered, is going to be greater during each successive time interval. And that's because the velocity is increasing. So therefore, we don't see a straight line here. We see a line that's curved like this, such that the slope is getting greater and greater and greater. Of course, remember that the slope of a displacement versus time graph is the velocity, so therefore the velocity here is less than the velocity here, which is less than the velocity here, which is less than the velocity here. So since the velocity is changing, then the slope of this line is changing, and therefore it's not a straight line.